You type google.com, hit enter, and in under a tenth of a second, Google appears. But here's the strange part. Your computer had no idea where Google lives. It had never seen this address before. So how did it find it that fast? Behind that instant load, your computer asked a question, and it raced through 4 servers across the internet. It came back with a number your browser could use, and all of it happened in under 100 milliseconds, invisibly. That process has a name. It's DNS, the domain name system, and it's one of the most elegant things the internet is built on. Every device on the internet has an IP address, a string of numbers like this. That's what your computer actually needs to connect. The problem: humans are terrible at remembering numbers. And these addresses change. Google has moved servers dozens of times. If the internet ran purely on IP addresses, you'd memorize a different number for every site and update it every time a server moved. In the early internet, it basically worked that way. One giant file listed every name and its address, the hosts.txt file, updated by hand at the Stanford Research Institute. By 1983, the internet was too big for one file. Paul Macapetris designed DNS as the fix, a distributed database that maps names to addresses automatically. The analogy is overused but exact. DNS is the internet's phone book, except it's spread across millions of servers and answers trillions of lookups a day. Every DNS lookup has 4 players. Meet them first, and the whole process clicks into place. 1. The recursive resolver. Your first stop, usually run by your ISP or a public one like Google or Cloudflare. It's the detective that does all the legwork for you. 2. The root name servers. 13 identities, labeled A through M, run by 12 organizations. They don't know where Google is, but they know who handles .com. 3. The TLD name servers. One set per top-level domain, .com, .org, .io. VeriSign runs .com. They point you to the domain's own servers. 4. The authoritative name server. The final stop. It actually holds the records for the domain. Ask it and you get a real answer, not another referral. Resolver, root, TLD, authoritative. Every lookup is a conversation between these 4. Now the full flow. You type google.com for the first time on a fresh device. Watch. First, your browser checks its own cache. Seen it recently? Done, no network at all. Then your operating system checks too, along with the host's file. Nothing cached. So the query goes to your recursive resolver, a tiny packet asking, "What's the IP for google.com?" The resolver asks a root server. Root replies, "I don't know Google, but for .com, talk to these TLD servers." The resolver asks the .com TLD server. It replies, "I don't have the IP either, but Google's own name servers are NS1 through NS4. Finally, the resolver asks Google's authoritative server. And this time, here's the A record and address with a TTL of 300 seconds. The resolver caches that answer and hands it back. Your browser opens the connection, all of it under 100 milliseconds. When the authoritative server answers, it's not just handing back a number. It's returning a DNS record, a type, a value, and a TTL. The A record maps a name to an IPv4 address, the most fundamental one. Quad A does the same for IPv6. A C name is an alias. It points one name at another name, not an IP handy for subdomains, but each one costs an extra lookup. An MX record tells email where to go. A TXT record holds free-form text used for domain verification, and for SPF and DKIM, which stop people forging your email. An NS record points to the authoritative name servers themselves. That's what the TLD servers hand back. And then there's TTL, time to live. How many seconds everyone may cache a record. Change one with a 24-hour TTL, and the old value can linger across the internet for a full day. The full chase, root, TLD, authoritative, takes real time. If every page load did all of it, the web would crawl. So DNS caches at every layer. Your browser caches first, then your operating system, then the recursive resolver. And that resolver cache is shared. When Cloudflare's resolver looks up google.com once, everyone behind it gets an instant answer: no root, no TLD, no authoritative. That's why popular sites resolve almost instantly. By the time you ask, the answer's been cached by thousands of requests before you. A brand new domain, cold cache. The full lookup runs, still under 100 milliseconds, just not instant. You've seen this error. Let's decode what actually broke. NX domain, non-existent domain. The authoritative server answered but said, "This name doesn't exist." A typo, an expired domain, or DNS pointed at nothing. Resolver not responding. Your ISP's DNS is down. This is exactly why switching to 8.8.8.8 or 1.1.1.1 often fixes internet that seems broken. Changed a record and it hasn't propagated. That's TTL doing its job. Old caches hold the previous answer until it expires. Not a bug, the design. And the dangerous one, DNS spoofing. An attacker slips you a fake address and sends you to a fraudulent server. That's why DNSSEC exists. It signs records cryptographically, so a resolver can prove the answer wasn't tampered with. So altogether, DNS is the internet's distributed phone book, names in, addresses out. 4 actors. Your resolver does the legwork. The root points to TLD servers, the TLD points to the authoritative server, and the authoritative server gives the real answer. Records define that answer: A, quad A, CNAME, MX, TXT, NS, and TTL controls how long it's cached. And when a site won't load, DNS is the first thing to check. 2 commands, dig or NS lookup, show you exactly what the resolver sees. Next time a page loads, the instant you hit enter, you'll know what happened in those 100 milliseconds. Subscribe for networking, explained visually, and tell me what to go deep on next.